Yeah.
This meeting is being recorded.
Okay. Move my slides. Yeah. Okay. Oh no, I went to the wrong place. Not this one. Yeah, this one. No. Where is the this is session 2. I was going to go on session 3. Yeah. Okay. All set. Hi everyone. Welcome to Learning Quantum Core for Applications. This is our session number 3 of the 6 sessions. And the first session and second session recorded sessions are available. However, I don't know whether where it has to be put. Currently it is in the Google Drive, but if necessary, we'll make it available on the what do you call the QML work group, the QML working group, meetup group, whatever we have. The either in the archive or in the chat or in the any document where we submit there, which is not submitted, I believe. So I'll work with Dr. Tupash to get that done there. So let me continue now. So we had session 1 where we did the overview of quantum, classical versus the current quantum, and what is the history that we covered. The second session, we looked at the quantum advantage. What is that advantage as far as acceleration and entanglement is concerned, and the maths and sign behind it. So we looked at some of the Pauli matrices, and we wanted to continue to extend that for superposition, possibly entanglement, yes, and then some Python code to look at. So today's session is going to be on quantum exercises. Of course, this is the core which we have been projecting, so that you have the qubits at the center of the whole course, and we surround it with the computational, the communication and the sensing aspects of it. And of course, this is brought to you by the QML meetup group along with the EOTF, the two organizations which have come together here. So today's goal will be to achieve, we make sure that we understand the Pauli matrix, which we started last time with a little bit more rigor, and see how we can use it for superposition, entanglement, and look at using Python, Google Colab, and you can also use Jupyter Notebook. So our goal will be to try to achieve these 5. And so the first we go into Pauli matrix. Pauli matrix are matrices, whatever we call. They are the 2x2 matrices, and they have some special characteristics because of which they are very much the part of quantum. So when you talk about a qubit basis states, the spin up and spin down, which are represented by bar with a 0 and a greater than, called ket0, bar with a 1 and greater than symbol called ket1, and the representation in the Dirac's notation is ket0 and ket1, which is a spin up and spin down. They are equivalent of a column matrix 1 0 and 0 1. Since we represent the what you call the superposition by a combination of linear combination of the basis states, which is for the standard basis, it is a 0 and a 1, or a ket0 and a ket1. We call it psi, which is the linear combination of ket0 and ket1. So we represent psi equal to alpha ket0 plus beta ket1, where alpha and beta are nothing, but if you square them, they correspond to the probability of the event being spin up or spin down. So alpha 0 plus beta 0 is equal to 1. So the probability is 1. But when we write the equation, we call it as alpha ket 0 plus beta ket 1. We don't write alpha square ket 0 and beta square ket 1. Rather, we write alpha ket 0 plus beta ket 1, where alpha and beta are the coefficients. They are complex coefficients. And so since they have they have a complex coefficient, we call it as C2, or the domain, or what we call as C2. So if you have two qubits, you will have two systems with states of qubits and combine them together. So the vector space which we project is always a xy, we would put it. And then if xy means just a surface basically, and the surface, so if you have one surface, you have one qubit. If you have two surfaces, you have two qubit. So the two surfaces then have to be a system A and system B, and we have to combine them. So at this time, I am only talking of a single qubit. Are you on? Yes, I am on. I hope you are getting. So, what I want to say is the Pauli matrix are 2 by 2 matrix, and they are called as, either you look at them as XYZ, or sometimes in rotational aspect they are looked upon as sigma X, sigma Y, sigma Z. Yeah. So this is the combination which we say sigma X, sigma Y, sigma Z. And there is an identity matrix which has a, so this is diagonal term, this is off diagonal term. Diagonal terms are unit, that is 1, and off diagonal terms are 0, that is equal to identity matrix. So identity matrix you have 2 by 2 with a 1 1 diagonally. Whereas the same thing, if you look at Z, just to remember, how do I remember? I is nothing, but we also call it as sigma 0. Now, if you have a matrix, these are all Pauli matrix, sigma X, sigma Y, sigma Z are X, Y, Z, like here see X and Z. So these are nothing but same thing, X and sigma X, sigma Z and Z are same, but they are referred as sigma X, sigma Y, sigma Z, or X, Y, Z. All these have some implication in the sense they do satisfy some of the properties, and that is why so uniqueness about Pauli matrix. If you are talking quantum, if you don't know Pauli matrix, it's like learning numbering without knowing the numbers. It's as good as that. So that is why we need to stress on Pauli matrices very well, very strongly, to remember them, because if you don't remember 1 plus 2 is 3, you can't do your numbering. Same way, at least to the extent, if you know Pauli's XYZ and what do they constitute, like if I square the matrix sigma X, last time we saw we got 1, which is the number. Same way, if you square sigma Y or square sigma Z, you will get 1. Now, how do I remember? Everybody asks. So unit matrix is very easy to remember. I or identity or sigma 0, which is nothing but a diagonal matrix 1 1 with off diagonal 0 0. Now same thing, you bring it here and just change the sign of this, which is -1. So you can derive from sigma 0 sigma Z by phase shifting, or just changing 1 to -1. So there is no change in the off diagonal and diagonal, except that the second which is 1 1. So this is 0 0 0 1. This is 1 0, and this is 1 1. So the 1 1 element which is there in the matrix, if you change that 1 1 to -1, you get a sigma Z. So deriving a sigma Z from I and remembering is very easy. And remember that Z is the, generally we call Z basis as the standard basis for measurements. Why we come to measurement? Because when you have a coin, example we always take with the spin of a coin. If a spin of the coin is in the air, you don't know whether it's a 0 or a 1, or a head or a tail. When it falls down to the ground, then you can realize that it has either fallen with head up or head down, or we call it as head and tail. So that probability is what is important. So from our point of view, what we have is a spin up and a spin down. Spin up is a 1 0, spin down is a 0 1. Now, the way to go about remembering x and sigma x is again easy to remember because it is identity matrix. You have off diagonal, you have diagonal 1 1, whereas in sigma x it's off diagonal 1 1, whereas the diagonal ones are 0. So if you remember I, you can remember x. If you can remember I, which is very normal, and then you can make out a sigma z with a 1 1 being minus 1. For sigma y to remember, it's very easy. It's whatever you have sigma x, you replace 1 by I, and in that case, if you put I, then the first I being minus, second I being I. So this is a bit odd, but this is what you have to remember, that minus I off diagonal, whereas 1 1 off diagonal is sigma x and sigma y, and sigma. So I'm giving you a logic how to remember, so that at least even if you can recollect, you are able to always remember what is sigma x, sigma y, sigma z, and sigma 0 or I, and the standard ket 0 and ket 1 with a column 1 0 and 0 1. So now let us look at the properties which are important before I move on to any of the quantum stuff. So ket x, if you say x, this is a matrix and this is an operator. And ket 0, if you operate, last time we saw that we took a operator x and applied it on ket 0, and we did a multiplication that is row with column and row with column for both of these. And because it is a 2 by 2 into 2 by 1, the resultant will be 2 by 1, and 2 by 1 means what? It's a column matrix. So if you apply x operator on ket 0, you end up with a 2 by 1 matrix which is 0 1, which is equal to ket 1. So when you apply x on ket 0, you get a ket 1. When you apply a matrix x, apply means you are doing a multiplication, really multiplication of the 2 by 2 vector with 2 by 1 vector. Yeah, it's 2 by 1 matrix, sorry, not vector. So 2 by 2 matrix by 2 by 1 matrix, and which results in ket 0. When you apply a x operator on ket 0, you get a ket 1. When you apply x operator on x operator means you are multiplying basically. So when you apply a ket operator x on 1, you get a 0. So this is very, very important, that if you have a spin up and you apply x, which is a not operation, you will get a spin down. So spin up, x operation on spin up will result in a spin down. And same way you can apply other operations. So the standard are in the standard basis, which is measured on z basis, we say that we have a ket 0 and a ket 1, which is spin up and spin down. Same way, if we change the basis of measurement from z to x, that means what? Our device, which is a example, if it is a magnetic dipole, then if you are holding the dipole in the x direction, z direction, that is the standard basis of measurement. However, if you hold it in the x direction, then in that case that is horizontal, then you are going to get a different results. Different results in the sense that it is not standard basis. The like we do spin up and spin down, we do have a corresponding equivalent called plus and minus. So this is all labeling at the end of it, but important thing is standard is always going to be 0 and 1 basis. That is ket 0, ket 1 basis. However, if you measure that measurement device or the appliance which you are using to measure, if you put it in the x direction, then you are going to get a plus or a minus. So you will have the standard at x basis will be plus, And then when you try to measure or when you apply X operator, it will turn out to be a minus. But what are plus and minus in terms of 0 and 1? That is very important. And that is nothing, but we'll see that later. But you remember, if you do X, if you measure in Z direction, which is vertical, as we see normally in the XYZ, remember that in reality, in quantum, the X and the surface is what is important. And that surface XY is visible to you because it is real. However, if it is not real, it is using complex number, then you cannot go into it and visibly see what is the way geometrically it is positioned. So because the numbers, the coefficients alpha and beta, which are square of which are nothing but probability, and if those probabilities are added, they become 1, and they are not real, they are complex, so we cannot see in XY. So usually there is a coincidence that we can represent 2 dimensions virtual space, which is not physical. Okay, real space is Euclidean XY, but if you have virtual complex in that, then it becomes a virtual space. So if you have a virtual space or virtual vector to represent, then we are forced to use, at least for understanding purposes, a 3-dimension way of looking at it, and that is called as block sphere. So block sphere is not real, it's just a coincidence that 3-dimensional presentation of qubit corresponds to the 2-dimension. However, it is not true beyond 2-dimension. It is very fortunate that we can represent the rotation of the vectors in 2-dimensional virtual space, which is Hilbert space, in a 3-dimension real space, which is the Euclidean XYZ. But you cannot do so if you have more number of qubits, because then it becomes quite complicated and you really end up in a very difficult position. That is why mathematics is important, and that is why Pauli Matrix is important. And we can see that it is easy to represent in terms of a bracket notation, like ket 0, ket of plus is minus, ket of minus is plus. Same way, ket of X operator on ket plus is you are getting ket plus, but X operator on ket minus is minus. So you can see here there is a operator does not impact the plus, but it does impact the X, because you are getting the negating of whatever is there. And this is because if you look for these numbers in the what you call the representation in the geometric, you will be able to appreciate these rotations, because magnitude wise there is no change, it's only the phase changes. So whenever we do any operation, any quantum operation, they are always unitary. And what is the definition of unitary? We'll come to that. But remember that X, Y, Z, these 3 are important from our point of view. And when we talk about X, Y, Z, these are represented by matrices, sigma X, sigma Y, sigma Z. And we do operation, so the square of X, square of Y, square of Z all turn to be 1. But however, when we multiply the terms which are not same, that means XY, instead of XY we do XZ, then Y is nothing but I of XZ. Same way you will go around and you can see a different combination. So this is for exercises, and I'm keeping this for your information. Let's move on to the superposition now. So in superposition, first thing before I go to superposition, I will just show you something which is important. So you have got a nucleus, a hydrogen atom, which has 2 electrons here. This is in the ground state, we call it ket 0, and this is one state, or ket 1. This is the excited state, ground state and excited state. So this represents a system A. Similarly, you got another system B. Now, can I distinguish between system A and system B? they are at the electron subelectronic level, it is hard to distinguish between two electrons, which are subatomic particles. But however, we have to distinguish by some naming them. Like if this is in one position and this is in zero position, then we can say, okay, I can understand this is system A, this is system B. But if both are in the same state, how are you going to distinguish? Is there any uniqueness in an electron that I can identify this is electron of A and this is electron of B? That's the confusion, or that is the problem we face. However, we try not to get into the what you call so much detail. All we say is there is a system A which has an electron which is in the ground state and can be excited. Same way, there is another system B which has got an electron which is in the ground state, can be extended or excited to by applying some kind of a what do you call energy, because it requires energy to move it from one state to another state. And that transformations are represented by the rotating vector or the point. If I have a circle, okay, there are people in the waiting room. Just a minute. How do I get them in? Give me a second. There are people in the waiting room, so I have to admit them. How do I join the admit? I believe standard basis states are measured. Yes, standard basis states are measured. I'm trying to get these people into the invite. No, admit all. Okay, sorry. I'm sorry. I hope others will be able to join now. Yeah, sorry. So I will continue where I was. Welcome, Cuba and Charles. Sorry, I was not able to look at the proper thing to allow you to come in. So let me move on now. So the what we were talking about is the two of the systems, system A and system B, with one electron each, and then said they are in the ground state and the excited state. And then we wanted to go back to make sure that these are what you call combined, and that combination was here. So I was looking at superposition. So if you have a single qubit, you have just the state 0 and 1, or ket 0 and ket 1, as we said. And we said the single qubit can be represented by an abstraction called psi, which is nothing but a letter with a bar and a greater than symbol, and which belongs to complex C2. That means what? It's a two-dimension complex space, which is nothing but a surface. So on a surface, you can represent these as a combination of alpha with ket 0 plus beta ket 1. So that's the representation of a vector psi, which is the Hilbert space, we call it. So in the Hilbert space with the alpha beta belonging to a complex two-dimension, we can represent the vector psi as alpha ket 0 plus beta ket 1, which is also to say that the square of these alpha and beta parameters, which are connected with the ket 0 and ket 1, equals 1. That means the probability of the toss, example, we talk about the toss of a coin. When it is in the air, you don't know. It can be alpha, beta. It can be alpha of 0 and beta of. That means it could be in the head in the state with alpha probability and 1 in the beta probability. So that's the interpretation to go with. Now, if you have two qubits, what happens? So I explained to you that two qubits means system A and system B, combination of system A and B. Then you have got each individual qubits having alpha 0, beta 0, alpha 1, beta 1, just to distinguish the two, because otherwise it will remain alpha beta, alpha beta. Probabilities are different. So when you have two qubits, they have different probabilities. They may be called alpha 0. Without loss of generality, we can call them alpha 0 and beta 0 and alpha 1, beta 1. So when we similarly, we can call them as psi 0 and psi 1 as the kit for representing those two electrons. And when they are combined, remember one very important rule. All operation in quantum are tensor products. So therefore, if you have a qubit which is psi 0, 1 and you have got qubit psi 1, so maybe psi 0 and 1, you can combine them and call it as psi 0, 1. 0 in the ms bit position, 1 in the ls bit position. So the combination of is nothing but a tensor product of the two. When you take a tensor product, it's nothing but a real time, all possible combination. So all possible combination, it comes to alpha 0 0, alpha 0 1, beta 0 1. So 0 0 0 1 1 0 1 1, all combination we put together. And when we put together, we can keep these kit 0 as normally we would do, or we can also do it as 0 0 kit. So that means you have 0 0 kit, 0 1 kit, 1 0 kit, or we can replace them with even decimal like 0 kit, 1 kit, 2 kit, 3 kit. But essentially all it means is it is all possible combination of the stuff which comes into picture, and that is what we do to be able to the tensor product we are able to take. So once we take the tensor product, then we get into the next level. So if for 2 qubit I do a combination, I get alpha kit 0 0 plus beta kit 1 plus gamma kit 1 0 plus delta kit 1 1, where alpha square plus beta square plus gamma square plus delta square equal to 1. So for a 2 qubit, you got 4 basis states. For 1 qubit, you had 2 basis states. So the normalization occurs by applying all 4 parameters of the 2 qubits, and the probability of them together having some state is equal to 1. Now, this we can drop the tensor product from. Most of the time, we don't even represent tensor product. We just remove that because it simplifies the complexity of writing and reading. And so generally we tend to drop the tensor product. So in a multi-qubit scenario, we can have a vector V1 representing A1 to A dimension, whatever the D dimension we have. And similarly, vector V2, we can have B1 to BD, D dimension. And when we multiply the vectors V1 by V2, that's what it is. Now, remember that the two vectors, they have an angle between them when we represent in a circle. Both of them are unity. So in quantum, because all vectors are unit vectors, as far as the quantum representation is there, that is, if they are part of the normalized vectors. So both V1 and V2, we can assume to start with that they are unit vectors. And when we try to do a dot product of the two vectors, that is the mapping of V1 on the V2 or V2 on the V1, either way, the mapping, whatever the map means, if you have XY axis, if I project on a X axis, there will be cos component. If I project on a Y axis, it will be the sine component. So sine cos component are trigonometrically, but in our term, a dot product of two vectors with an angle theta, whatever may be the sine cos, you will always end up in a scalar. So dot product stands for inner product. Whereas, so if you have a matrix, which we can represent, matrix representation is equally valid, as we said, for the kit 0 and kit 1 as the column vectors. So if you have two vectors and if you have a dot product of the two, which is nothing but the angle between the two, they only differ by phase, by magnitude, they are always unity. And therefore we can represent, if we have a standard basis, a qubit Sn, which has xi, where x belongs to 0 or 1. So x can be 0 or 1. So this is basically, we are talking about a vector where we can have a dot product, and when we do the dot product, we get a number which is scalar. And that's the important factor to remember. Standard basis is always Z basis, we call it. And second basis, X basis, is referred as Hadamard basis. So there are two bases. One is the standard basis, other is the Hadamard basis. There can be another third basis also. You can take it, or you can take any vector n in the n direction. It can be in any direction. But X basis is your Hadamard basis. And that is represented as 1 by root 2 of K0 plus. So if you take a plus basis or minus basis, and if you represent them as if in the Z basis, then Z basis representation is K0 and K1. It turns out that your plus basis is equivalent to plus. If you have a plus, then you will have 1 by root 2 K0 plus K1. So basically, we can transform whatever is in the X basis onto a standard basis if we apply this. And this is true depending on, when we saw that we transform X plus, we get a plus. But if we transform X minus, you get a minus. So that is why this, one of them is plus, the other one is minus. So measurement can be standard, and this is based on the device you use, and a device or the appliance we use for measurement. And if it is parallel to z-axis, then we call it as standard basis. If it is parallel to x-axis, because if you have some magnetism example as part of this, the north to south, if there are polarization, if it is the horizontal and vertical polarization, if you have a device which is perpendicular and parallel, if you do not have a component on both vertical and horizontal basis, then you will not get any number. So if it is vertical, you will not get horizontal. If you are horizontal, you will not get vertical. But if it is somewhere in between, it's neither vertical nor horizontal, then it is at some angle, then there will be a sine cos component. And correspondingly, the device that is used to measure will show up some of these, which is some percentage. It could be 50%, 40%, 20%, but it will not be same as 100%. So that's the key here. So let me now get into real tensor product here, which is very important from our point of view. So you have a system A with 1 electron, you have system B with 1 electron. When you combine the two, which is in the Hilbert space, what we call Hilbert space 1 and Hilbert space 2. So space-wise, we are looking at, you have two vectors, u and v. The possibilities are humongous. That means if you have two vectors and you call it as u1 and u2, and if you are going to combine with v, then you are going to get u1 plus u2 into v, which is nothing but this cross which is shown is tensor product. So tensor product of two vectors, instead of having 1 electron, if you had 2 electron and two vectors representing them, then if you multiply with the third one, or tensor, you take a tensor product with the third one, that is what the laws of this is distribution, association and distribution, all these laws are applicable. So therefore u1 plus u2 into v equal to u1 into v plus u2 into v. Same way you go the other way around, u into v1 plus v2, and then you are going to get the u v1 plus, is same thing as this. So essentially what we are trying to say is, if you have a K0 and if you have two K0, you are doing a cross product. That is nothing but, this is in space 1, this is in space 2, and if you take a cross product of 2, you can either write as K0 K0 or K0 0. So K0 K1 is equivalent to K0 K1 is equivalent to K0. So these are tensor products. So we don't write the in between the tensor sign. It's simply we cut them together, because as I said, if you have 2 electrons, you can't distinguish actually which is which. But for us, we need to have distinction which is ms bit and ls bit, and therefore our ms bit, if you have this is q1 and this is q0, our q1 will be always be ms bit, q0 will be the lower bit, or which is the representation in terms of electrons. So idea here is the Hilbert space is a special 2 to the power m dimension vector. So if you have got many number of electrons or many number of qubits equivalent of that, then you can multiply those spaces, vector spaces, which are virtual, not real, because real means it's Euclidean, then you get xy. If you don't have real, you have complex number, you are going to get complex of 2 into complex of 2. So you can say the Hilbert transform deals with the plus minus pi by 2 radians. So usually when you represent in xy, pi radian is 180 degree and pi by 2 is nothing but between this and this. So if I draw xy, fortunately, even for a that is complex space, we can represent them within the pi by 2 radian. So what it means is you can try with a plus pi by 2 plus minus pi by 2 radians. So pi equal to pi radian is 180 degree, pi by 2 is 90 degree. So you can say within plus minus 90 degree, we can show the transformation. So the tensor product are really contained within the specific radians, which radians means the angle which we are trying to show. And that's the important message here, that you can apply all the mathematical operation which are applicable to the vectors to this Hilbert space, and therefore it does support the associative law and the distributive law, and that is important. And the notation used are a little bit complicated or simplified in our terms, because you cannot keep on writing every time ket 0 cross, that is the tensor product with ket 0. Instead of that, we can use this or this. Either of them is equally good. And even we can change that to numeric instead of 0, 1. We can put it as a digit, 10 digit decimal number, 1, 2, 3, 4, 5, 6 also, ket 1, ket 2, ket 3, ket 4, etc. Now, before I move to this, I'll have to show you something which is in normal binary, in our classical computer, what we do, we say we have 8-bit register. We've got 16-bit register. We've got 32-bit register. There the question is, we have, because they do mathematical operation, mathematical as well as logical, but for most of the mathematical operation, you need a carry forward. So if I add 55 plus 55, I have to say 5, 5, 10. So that gives a 0, then carry forward 1. Then I say 5, 5, 10 plus 1, 11, right? So this is the challenge. We don't have any carry forward here. All we have got is a qubit, the state, and then operate on the state. So therefore, in the terms of quantum registers, you don't have that kind of a carry forward registers. You only have registers. That means you got individual qubits. How you use them, that depends on the algorithms. But you have qubits, 1 qubit, 2 qubit, 3 qubit, 4 qubit, 5. Let me just go through so that you understand what is so critical about this. So if you have 1 qubit, you have got 2 basis vector states. How many other mixed states? There are no mixed states, because you have 2 qubits, they are mutually exclusive. That means they are orthonormal. That means they are orthogonal as well as normal. They are orthonormal. And so if one exists, the other doesn't exist. So there is no question of mixed states here. However, when it comes to 2 qubits, now you are dealing with 4 basis vectors. And once you have 4 basis vectors, the number of mixed state, how many it will be, that will be, because it's always the permutation, not the combination. Permutation is n to the power n. So if you have got 4 basis vectors, 4 raised to 4, 4 4s are 16, 4s are 64, 4s are 256. So now you have got 256 permutation. But out of 256 permutation, 2 to the power 2, which is 4, are the basis So remaining 252 permutations are the mixed states. So majority of the states are mixed states, whereas minority of the states are basis states when your number is low. Okay, even when number goes high, n to the power n will be the all possible states, out of which you subtract the 2 to the power n, then you will get the mixed states. Now, out of the 252 states which are mixed states, there are 4 permutations called Bell states, which are the ones which are entangled. Very popular, and we'll come to that. But essentially what I want to say is, in terms of number, you understand that permutation is bigger, combination is smaller. So that is the reason if you have 3 qubits, the number of state is 2 to the power 3, which is 2 to 4 to 8. So 8 are basis vectors, but because there are 8 bases, then you can n to the power and 8 to the power 8, that will come out 16,000 some number, which you can see here. So the mixed states are plenty, but the ones which are important to us are entangled states. Majority of the mixed states, which is combination of the basis states, in terms of permutation, they are high. In terms of combinations that work out entangled for us to be capitalizing on, they are limited. So this is the space. Very hard to understand, but remember, C2 is the complex 2-dimensional, complex 4-dimensional. When you come to 3 qubits, then you've got complex 8-dimension. And so complex 2 to the power n minus 1, 0 being the first, therefore you have to subtract 1. So you can see that this is the number of combinations possible. And not only that, when you always measure in terms of z basis, the vectors or the representation can be like 0, ket 0, ket 1, or it can be ket plus, ket minus if it is not z basis, if it is going to be on the x basis, or if it is going to be on the y basis, it can be ket I minus I. These are the 3 representation, but basis, z basis is always going to be the first. So 0, 1, 1, 0, 1, 1. This is MSB to LSB. Same way, here I have represented a z basis, x basis and y basis, but here I have not written any of the x, y, z basis. It's all z basis. So in z basis you got, or the standard basis, you can call it standard basis instead. So standard basis is 0, 1, 1, 0, 1, 1 kets. Similarly, ket 0, ket 1, ket 2, ket 3, ket 4, ket 5, ket 6, ket 7 for a 3 qubit with a 8 basis states, and so on and so forth. So why I brought this before even I talk about anything else is because one has to understand that there are many more mixed states than the basis states. And there are some of them entangled. Entangled, we'll come to the definition. Definition of entanglement is if you cannot factor it further to the basis states, then you are stuck because you cannot further factor it. That means you cannot bring it in terms of this single pure states. These are pure states. So if you cannot get to the pure states in a 2 qubit, there are 4 pure states. In 1 qubit, there are 2 pure states. In 3 qubit, there are 8 pure states. If you cannot express a combination in terms of pure states alone, then they are mixed states. And that's the definition of mixed state. And that mixed state may involve entanglement, may not involve entanglement. That I leave it to that. So let's go back to our, one sec, we have people waiting in the, let me admit them. So where is Punyu? Okay, how do I enable them? Give me a second. Admit, how do I admit? Sorry. Enable waiting room, or I can disable waiting room, right? How do I admit? Give me a second. 2 new messages. How do I enable stop? I'm stuck with this now. How do I enable? How do you calculate the other mix? How do you calculate other mixed states? We don't have a calculation for it. I only have the number for it. One sec, let me see. How do I enable people? Is there anything that can help me enable? Sorry, I don't see how do I enable it. This is weird. Okay, let's assume that I'm able to enable them. Enable all participants. Can I not make it by default? Enable all participants. Pause, no setting. I think I cannot do much in that. Okay, let me leave it there. So let me continue on the thing while I am able to. Can I not make somebody host in this? No. If I make host, then I will lose the. Okay, no problem. Let's continue on our journey. So we have another few minutes. So let me just cover the bit flip. So if you give alpha ket 0 0 alpha 0 ket 0 plus alpha 1 ket 1, then you do a NOT logic on that, you get a first one passes without ket 0 with no change. That ket 1 you are getting a, you can see that alpha 0 goes to 1 whereas alpha 1 comes to 0. So basically bit flip implies that when you have operator x, and if you apply to the spin up and spin down, you can get a ket 1 and a ket 0, which is nothing but ket 0 gives you ket 1 and ket 1 gives you ket 0, and therefore correspondingly when you do a x operation on a linear combination or a psi equal to ket 0 plus ket 1 1, you get a alpha 1 ket 0 plus wave. So that means the coefficient interchanges for 0 and 1. So qubits have both amplitude and phase. In this case, you can see that the amplitudes have flipped along with the corresponding kets. So ket 0 has got a now alpha 1 as the parameter, whereas ket 1 has got alpha 0. So this is a amplitude probability which is there, the flip. So this is what the bit flip it is called. And the phase flip is nothing but very similar, except that only one of them changes. Like if you take a z and you apply the matrix and then derive, then you get whatever is ket 0 remains as ket 0, but ket 1 becomes a ket minus 1 by the operation of z. So z operation leads to a phase flip, whereas X operation leads to an amplitude flip. So bit flip and phase flip are the two important factors which we need to remember. And the last of this one today we will cover is Hadamard. What is Hadamard? Hadamard, now these are all called as gates or poly. So either you call it as poly X, poly Z, or you can call it as X gate and Y, Z gate. The reason why we call it this gate is we are going to deploy them as a quantum gates. And so bit flip, phase flip, and Hadamard transform. Hadamard transform is any transform is in terms of quantum is always a vector turning. So if you represent a vector V as one of the participant, then if it is turned from V1 to V2, it has moved, rotated around the square, rotated around the xy axis with a z, with a endpoint at 0 at the middle, and it has moved in the pi by 2 whatever radian that is in the first quadrant of the Euclidean xy coordinate space by certain angle, and that angle is which is what the phase shift is. But in essence, what has happened is it is just unitary. So that means your product if it was starting, like example, if you have an operator called 1 by root 2, 1 by root 2, 1 by root 2 minus 1 by root 2, which is the Hadamard transform or operator we call it. If we use a Hadamard operator on a particular example, K0, then we are doing a Hadamard of K0, and K0 is represented, in this case H is represented by 1 by root 2, 1 by root 2 minus 1 by root 2 as the operator, and K0 is represented by the 1 0, which is the spin up. And this is, when you multiply this, you get 1 by root 2, 1 by root 2, which is nothing but 1 by root 2 of K0 plus 1 by root 2 of K1, which is equal to plus. Same way, if you take a K1 and you operate a Hadamard on a K1, K1 is represented by a column matrix 0, 1, whereas the Hadamard operator is represented by 1 by root 2, 1 by root 2, 1 by root 2 minus 1 by root 2. When you do the operation this way, which is what we do, there is row column multiplication, you end up with a 1 by root 2 and minus 1 by root 2, which is nothing, Ket minus 1. So the idea here, what this representing is that if you have a Ket0, you put a Hadamard, apply a Hadamard operation on it, you get a plus of it. When you have a 1, you apply a Hadamard, you get a minus 1. The reverse is also true. If you get a plus and you apply a Hadamard, you get 0. If you have a minus, you apply a Hadamard, you can get 1. So this is very important, and this is what is represented here. Ket0 here is represented as 1 by root 2 of Ket0 plus 1 by root 2 of Ket1. Same way, here we have 1 equivalent, 1 by root 2 Ket0 minus 1 by. So these are symbolically represented at Ket plus and Ket minus, but they are the corresponding to what is in X, what is in standard basis Ket0 and Ket1. These are the standard basis in X. So Hadamard transform takes a given basis representation and converts it into another basis. That is, from X to Z or Z to X, you can operate a Hadamard. Hadamard also is a way of creating a superposition, and that we will see later. But important, I wanted to cover bit flip, face flip, and Hadamard. These three operations, along with the tensor product, this was our goal for today. And this is for 1 qubit or 2 qubit or n qubit, it differs. So if I call a unitary matrix, unitary gate as a matrix of A, B, C, D, and if I take a U dagger, which is nothing but complex conjugate transpose of it, then you get A bar and D bar as is, but C, D flip, and they become C bar and D bar. So you can say U dagger. So U dagger, if you multiply these, you get a I, or the I matrix, nothing but 1. So basically, the complex conjugate of a matrix is nothing but a mirror image. So when you take a mirror image of it and then you have a multiplication here, you will get a transform. So basically you are trying to transform, and it is nothing but an identity. U dagger is equal to identity. So unitary matrix is one defined whose complex conjugate with itself is a identity matrix. In fact, this is the definition of unitary. And you can have example here, the simplest to see if you got n dimension. So example, 2 qubit gate, you can have 2 inputs and 2 outputs, and you can see the combination. So this is the transformer which transforms this into this, and here we have just put a prime alpha 00 prime, alpha 01 prime. Here is alpha 00. So this is to represent a 2. This is 1 qubit gate. This is 2 qubit gate. You can have n qubit gate, and as many you can have. But remember, the first column ABCD, whatever is there, that is the one which will reflect for the product. And we can, what it means is that only diagonalization matters for the base, for the basis vectors, which is nothing but gives you a matrix with one diagonally So we have off diagonal, diagonal. I mentioned to you in 2 by 2. It can be same in 3 by 3 also. So important thing to remember is that you get a column vector representation of the inputs. You get a column representation of second, and if you have one and you apply unitary, they are nothing but they are same in magnitude. However, they may have a phase difference, and the phase flip is something which we will study later. But at this time, magnitude wise, you can take any unitary matrix and take any of the input combination of number of bits, like we discussed in the previously, that 1 qubit, 2 qubit, n qubit, whatever qubit combination you take, you will always have a unitary output because they are normalized. And this probability is applicable in only in case of a, that is why we put the term alpha, beta, gamma, delta, etc. But the square of them is what the probability is. Otherwise, these are complex numbers. You cannot measure unless they are collapsing. And therefore, we just say square of them is equal to 1, which is the probability. So at this stage, I think I am going to probably just show you one before I wind up. So here is a Google Colab. Google Colab is a what you call a notebook, and this notebook has got we have some codes here. All we are trying to say is how do we use the vectors. So finding eigenvectors is an important exercise. So what I'm going to do is simply show you how we can use Colab, which is Google Colab notebook, along with the NumPy libraries and some other libraries which are available in the linear algebra. And those are the ones like you have scikit-learning. So these are some of the libraries which are used for vector or array multiplication. So here we have got import numpy as np. This is the Python. So you are taking the numpy, and then you are taking the array, and then you are initializing the values for the vector. For the example here, we have 1 comma 1j, that means 1 plus 1j as one number, 2 plus 1j as j. In this case, j stands for I is the imaginary. In case of Python, here we use j instead of I. So that's the reason you have.
Excuse me, Prakash.
Yeah.
Are you showing your notebook?
Oh, okay. I see. I'm sorry. Yes, I'm showing my notebook. Probably I missed that. I have to reshare. Okay, sorry. Stop share. Gosh, share, and then I have to do. Okay, I thought it will come up automatically. It didn't come. Okay, now you are seeing. Ron?
Yeah, I see it now.
I'm sorry. I missed that point. But anyway, so I'll again repeat. Here we are talking of a NumPy as a library which is used for vector operation. And Jupyter notebooks are available both from Google, from IBM, and from Anaconda, different ways of using it. I am using Google Colab to just demonstrate to you that what you can do for vector operation. So here what we have is a normalizing vector, which is if I take a vector v1, if I normalize it, how do I normalize it and what is the value I should give? So here is a vector v1 which is represented as an array under NumPy library, which is represented as, in this case, I have taken 1 comma 1j, that means 1 plus ij, or 1 plus j, you can say it, simplify, or 1 plus I if you are using I instead of j. Same way, this is 2 plus I, which is equal to 2. So we have array of 2, which is what the points in the space. So if you have 2 points, you can draw a line and direction, and that's what we have. So what we are trying to do is we are having a vector v1, and then we try to normalize using the scikit. So what we have is we first define an array, initialize the array, print the array, and then So when we initialize the array, you can see that here is what we are seeing the vector. And then once you print it, this is what you see. And once you try to normalize, normalization is what, say, let's call it a normalized V2 is the vector which is normalized V1. So we have to take V1 and apply the linear algebra normalize library function V1. And so linear algebra dot normalization of V1. V1 divided by that produces the V2, which is the normalized vector V1. And then we can say print this. So when we do this, you can see here the results. So essentially our attempt has been, if you normalize a vector, it should always be unity. And this is what we are seeing. So taking two vectors, 2 points, then normalizing them using the various libraries, 0.999999 is nothing but it's a 1. So basically when you normalize a vector, it will end up in unity. That is the principle here. And this vectors dot whatever the code is there, this is available to you. I will share that with you. And same way we can do a eigen vector. So generally when we do a measurement in quantum, we want the result to be either plus or minus 1, because if the eigenvectors are plus or minus 1, then it is easy to interpret, which is interpretation in terms of numbers. Whereas if we have something different, then it will be difficult to interpret it. So all testing require that eigenvector be some value which is measurable. So in this case, we have taken plus and minus 1. And to get the plus and minus 1, which is the eigenvalues here, you can see we have applied the numbers. In this case, 0 minus j, which is minus j, and 1. The other one is 1. So minus j and 1 are the two endpoints for which we have tried to analyze and get the eigenvalues and the eigenvectors using the NP linear algebra eigen of sigma y. So we have taken sigma y equal to this minus I and j, which is minus 1j and 1j. So basically these are the two numbers represented as sigma y, and we have tried to get the value of it. So basically I and minus I are equivalent to j and minus j. That's a sigma y. So we have taken the sigma y into array and tried to get a eigenvalues and eigenvectors using the library, and then we got it as minus 1 and plus 1, which is what we expected. Whereas the vector itself is combination of all being 1 by root 2. 1 by root 2 is 0.0707, and that is what it is turning out to be. You can see 1 by root 2 all the way, except that one of them is minus, which is what we know: 1 by root 2, 1 by root 2, 1 by root 2, minus 1 by root 2. So this is the representation of a vector, normalizing of the vector, and besides that, the calculation or the derivation of the eigenvalues and the eigenvectors. So this is a very, very important terminology used, and we are already 15 minutes past our time. Because we started a bit late, I could get this. Hopefully we have got everything recorded, and the recorded can be presented. Those who I could not enable, my apology, because what happened was, if I take sound on my Chromebook, it doesn't come well and it doesn't record. So I lost one of the first recording, which I had to re-record using a different tool rather than Zoom. But this one I am doing on Zoom. Hopefully those who missed the call or who I could not enable, they will be able to see the record, and this will be session 3. So I think I have sufficiently covered the minimum that is required, what to do to calculate eigenvalues, eigenvectors, and also normalize and orthonormality. So these are the things which are very important, and hopefully if you are able to do this much exercise, then I think I can move on to the next on the both on the quantum circuits, their optimization, algorithms, and their optimization, which we'll cover in the next 3 lectures, and hopefully that will be able to give us enough exercises to be able to certify you as qualified based on the 6 lecture sessions we are conducting. Okay, and hopefully we will have some time period which we'll give after 6 weeks to be able to complete in 2 to 3 weeks, because I know some of the lectures could not be attended by you. And so the exercises I'll follow with this. I think I will end the call unless you have any questions. So Ron, any questions from anybody, please? Charles, Shubha, anything you want to ask? Please do ask. And,
Yeah, you referred to the standard basis state as being the Z basis.
Correct.
I'm not sure that's correct. I believe most of the literature refers to the standard basis as being the X basis, and it's related to the fact that the standard bases are rotations about the X axis. And when you go from a cat 0 to a cat 1, you do an X rotation. So people might, I believe that's the case. I may have to investigate it, but you might find.
Yeah, I checked that, because my understanding was Z basis is what is the standard basis. The Z basis, when we say it is on the block sphere, right? Now, if I have to go by XY axis, there is no Z here. So it has to be X basis in that case. I get your point. But how did I interpret this is a bit of a challenge for me, because remember, there is not, you are right. It has to be X basis. I'm very X basis on XY Euclidean basis.
When you take a state vector for just one qubit and you project it onto the block sphere, you're projecting it onto a polar coordinate system.
Correct.
So that's why you measure the standard basis is measured as a rotation about X. Even though all the shorthand bracket stuff eliminates all that crap, but that's what I believe.
So this is the problem. What happens is most of the people start believing, including myself, into block sphere. I think block sphere is a misnomer in the sense that it does not, because we do Z basis right there. Everything is Z basis. X and Y are just a basis of showing the rotation. But if you go by what you said is right, because XY basis, I will stand corrected. I will remove that Z basis everywhere. I just say standard.
I understand.
Yeah,
I understand the Z basis to be the plus and minus bases, which are the Hadamard results, and the I plus and minus I to be the Y basis. Again, it's because it's based on what axis you have to rotate about to get the change.
Correct. Okay. So I stand corrected. I will correct it, and instead of Z basis, I will start calling it standard basis, because standard basis is what is the XY.
Yeah. And if you just leave it that way, you'll probably be fine.
I think
for the most part, everybody, when they hear standard basis, they understand that's like in Qiskit or IBM or any quantum land. When you do the measurement, you're measuring on standard basis. That's all that's really important. So.
Yeah. Correct. Because see, initially, one more problem I faced with this was when I started with block sphere, XYZ, you got then the Z basis, X basis, Y basis is also there. Nobody ever has told about Y basis. That was wonderful. I was wondering about it. Then I realized there is no Y basis. There is standard basis.
Well, you can't. Yeah, there's no way to measure in the basis, but there is a Y basis. It's the plus and minus. It's the plus and minus I basis. Correct. And you can do a transform. You can project those bases back onto the standard basis to get a measurement. But you're right. Those are rarely used because most of the algorithms are only interested in the X or the X or Z, and the Y is the Y is usually where your phase is encoded, and that gets all scrambled out when you do the measurement. So
it's in the complex space, so we cannot really evaluate I and minus I. You only can transform into it. Physical wise, you cannot measure them. So that is why the standard basis X basis, the other is phase Z, which is still a basis.
yeah.
So I agree with you. I have to correct. I will
okay. And you're getting this information from that same book you're working with. Which can you do you have the title of that again?
So the two, see, this I have not based on the book. All this I have based on various university lectures, UCSD lectures, and UC Davis lectures. But previous one, the other one which I am running it on the book basis. And I'll give you the book reason, because somebody wants to buy that book. Welcome, because that has got a real good. This one, let me just pull that out for you. Yeah. So here is the book. I hope you can see this. I'll just put it in the you can see the book here. Yeah, I will just refer this book in our presentation also, so that here we were.
You're still present. Are you showing on camera? You're still present?
I stopped sharing. I'll stop sharing and start sharing the correct one. One sec. Give me a second. So I have. Where is this? This is here. Yeah. Okay. So I am putting in the chat window here the link to it. Hopefully, people can pick up from the book referred here, Springer book. You can pick up from there. And the other one, what I will do is I'll also put that book because I have not referred as shared book, but I can do that. There is nothing wrong in that. You can always put any book you want to refer. So I'll do one thing. I will add that book here. So you can use this. Okay, I have to share that before I tell you where it is. So give me a second. I will just make sure that you are here. Yeah. So I will share the screen before I close. And this is the one. So can you see the shared book referred in our slides? Slide 12. Ron?
Yeah, it's good. Thanks.
So I have added that. And what I will do is whatever I have done today, I will just re-record it with the removing Z basis as standard basis as the first basis, so that we do not have that creeping in altogether again and again. So that I will do. Even though we have recorded here, I will re-record this one to specifically correct that, so that we don't propagate a wrong notion. And Ron, thank you for catching me on that. And let's hope. Any other person, any questions? Shubha, anything from your side? Okay, I think I will close this. I have the recording, I have the slides. Now I will talk to Dr. Tupash, or I look at the, I think it is using some, what do you call the GitHub. And I'm not comfortable submitting to GitHub because I don't have the way to access it. I'm not sure how I'll do it. But if that is the only option, fine. Otherwise, I'll put it in the YouTube if they have one. If the this group has any YouTube, then I'll put it in that YouTube accordingly. Okay, I'll get it posted there so that you have the recording of 2. The third one I'll re-record, put it, and then we have everything in place. And Ron, if you want to present anything, let me know. Most welcome, especially the optimization. If you want to do some exercises and optimization, I would like your input to that. Or at least you can even present it if you can. Let me know.
Yeah, well, all my summer schools are finishing up, so maybe in the next couple months, we'll see.
Okay. Otherwise, I'll run through you the optimization portion of it, because I do not have a complete understanding of that at this time. I'm still trying to learn that. Especially they do wire cutting and they talk about circuit cutting, which is there in the part of their beta. And I'm still grappling with that. How do you reduce the width and the depth of the circuit, etc.? So that might be of interest. If there is something common we come across, definitely you are welcome to do that. Okay. And with that, I will close today's session. And hopefully we have done what we can to justify, because we want to make sure that this runs in a proper way and everybody gets to the level what one is looking for. Okay. Thanks everyone. I will close the session then. Thank you.